We'll continue to explain the supervised tutorial by Clement Farabet. Now we're at step 3 and we're basically introducing the loss function that is used to minimize in training of this network. So now that we have a model, we can define the loss function. So this loss function is minimized across the entire data set N. And one of the simplest functions that one can minimize is basically the mean square error between the prediction of the model and the output of the network. So Y is it could be the output of the model and T are the labels. In Torch, you can just say criterion equal neural net package MSA mean square error criterion. It's a very good loss for classification, and it forces the model to predict exactly the values imposed by the label. But for this reason, it might not be as good as a classification, but it might be good, for example, to do curve fitting or something like this. So for classification, sometimes, most usually people use probabilistic objective, like the log likelihood, something that gives you some kind of a probability at the output that the object that you see is actually belongs to this category. So this is basically achieving by feeding the output units into a softmax function that turns the linear regression to a logistic regression. So you can get the outputs of the network plus the bias term into a softmax, and this basically turns it into a normalized probability. You can then minimize the final prediction by taking the argument max of this distribution, not the minimum, not the maximum in this case. And the output of any model can be turned into a really normalized log probability by just adding this softmax function on the top. So one can simply do model add and n.log softmax if you want to do this. If you want to minimize this data set instead of maximizing it, you can maximize the likelihood that the correct class for each sample in the data set. You can also minimize the negative log likelihood, NLL, or also minimize the cross entropy between the prediction of our model. So this is similar to the computation of entropy. So minus log of the probability. This can be done in Torch easily with class NL criterion, which gives you a vector of log probabilities to be the correct class. There's also another kind of multi-margin loss that is quite similar to the score vector machine loss. This is called multi-margin criterion. So these are the possible options that one has in recording, in using basically loss function in Torch. We will now go into training. We'll look at the training procedure. I won't go into too much detail about the training because it employs a complex technique that are beyond the scope of this class, and I'll leave them to the students or interesting people to study them. The training file, though, it's quite nicely optimized for these things, so I recommend you just use it. So it's a Ford file called fortrain.lua, and what you need to do is that since a lot of these problems with the ComNet is the implementation of problem is not really complex anymore. You really need stochastic estimation of gradients or stochastic gradient descents, which has shown to produce much better generalization results for several problems recently. So we explained a little bit about stochastic gradient descent, or SGD. There are other techniques that are used in these training samples that are more sophisticated. We don't want to go into details, but one can study them if he's interested. Also, you have to notice that it's very important to use stochastic. It's very important to start with a few epochs of the stochastic gradient descent before you try to go into more complicated. And because of your non-convex nature of the problem, at the beginning, training, random initialization, the landscape might be highly non-convex, and so it's hard to make assumptions. So other complicated technique might not work. So often SGS is the best we can do. Batch methods and other things can be used more safely. So we really, for the scope of our class, we really try to keep on stochastic gradient descent because it's a really easy technique and it gives you good result, even though you might be able to optimize them better later. Stochasticity is also very important in stochastic gradient descent because it allows faster, even though rough convergence. So even though you don't really get to the best minimum, which might not really exist, might be like a mathematical construct for very complicated problems. If you try to categorize many categories and things like this, you might not be able to really find it's just one minimum, but you can. It's much better for you to settle for a faster convergence. So this is the final file for training. It's in here. You can set up different classes. You set up a confusion matrix that you can output every now and then just to figure out exactly how you're doing and what things are getting confused for. So sometimes it's very nice. For example, if a 3 and a 8 could be confused, or a 1 or a 7 could be confused if you're writing letters. Sometimes this tells you exactly what's going on. This is the function training that has all this. It's optimized with all the tricks from Clement Farabet. But we're going to try to use it in the simplest form. So the function train has an epoch, so you can run an entire data set multiple times. It has a progress bar. What you do is you usually create a mini batch. So you do a small batch of gradient descent on. You don't do an update on every sample, but you maybe update every 10 samples or so. It usually gives you better results. So you take a bunch of these inputs. They are obviously shuffled. You really need to shuffle all the data. And then you evaluate the function and its derivative. Basically, figure out the derivative so that you can do gradient descent. So you set all the parameters, you copy them, you set the gradient to 0, and then you evaluate the function model, you go forward, and then you evaluate the error with the specific criterion, and you do the backward step, so forward step, backward step. Then you update the confusion, you update all the derivatives, normalize all the gradients, and then return the gradients and the parameters. Here are all the optimization steps that you can do that we're not really going to do too much beside the stochastic gradient descent. And you can then take a clock to check out how long it takes you to train one epoch. You print the confusion matrix, and you print the accuracy and so forth. You can also save the network if you are inclined to do so. And so that's basically the training set. When you're done, you just while through you train. The other thing that we will end up is the other step number 5 is to test the model. So this is very similar to that training procedure that we've done. So there's just basically very simple testing procedure that goes test over all the data. You do a forward pass of every single input, and then you create a confusion matrix. You again check the time, check the confusion, and plot all the results. And that's basically it. That's the most important thing about this supervised training. And we have to thank Clement Farabet for putting together this very nice tutorial.